In this video, I'm going to look at how we calculate the pH of strong bases. And by strong bases, I mean substances like potassium hydroxide, sodium hydroxide, calcium hydroxide. In other words, metal hydroxides. If you remember back to something we said in a previous acids and bases video, strong bases are fully dissociated when they're in aqueous solution. So I've gone for the first one here, potassium hydroxide. So when that's in solution, it will completely dissociate into its ions. And obviously it's this arrow, this single direction arrow, which indicates complete dissociation. So rather than tell you the answer straight away, I'm going to get you to think how you would do this. So I've put on there that this potassium hydroxide, let's suppose it was 0.1 moles per decimeter cubed in concentration. Can you work out the pH of this solution of potassium hydroxide? A couple of hints for you. Remember, to calculate the pH of anything, we need to know the hydrogen ion concentration. And the other thing is we're going to need to employ Kw. And I almost forgot to say that the temperature is 298 Kelvin. Let's see how you get on. So because this is a strong base, the full dissociation in this 1:1 mole ratio means that the concentration of hydroxide ions will also be 0.1 moles per decimeter cubed. I did say in the clues that we'd need to use Kw, so there you can see the expression for Kw. And because this is at 298 Kelvin, we know that this will be 1 times 10 to the minus 14. So ultimately we need to know the hydrogen ion concentration, but we do know the OH minus concentration. So let's take that over to the other side, and that should give us the H plus concentration. So we get H plus concentration is the Kw value divided by the hydroxide ion concentration, and that comes out at 1 times 10 to the minus 13. So we've got our H plus now, so we just minus log that, and we get a pH of 13. So we'll just finish with 3 typical questions you might be asked on this. First two, find the pH of some strong bases at 298 Kelvin, and the third one is kind of working the other way. Calculate the hydroxide ion concentration at 298 for a solution whose pH you're given as 12.43. So for the first one, we need to use the Kw expression. So we'll rearrange to get H plus concentration on its own. So H plus concentration is the Kw divided by the OH minus concentration. So we've already put the numbers in, and it comes out at 2 times 10 to the minus 12. We're just going to minus log that now, and we get, well, there's the value on my calculator, 11.698, so we'll go for 11.70. I've been a little bit sneaky with the next one. I've used calcium hydroxide and not sodium hydroxide or potassium hydroxide. And so remember, this contains 2 hydroxide ions. So if we know the concentration of the calcium hydroxide, the OH minus concentration will be double that. So it's actually 0.0712. So when we feed that into the rearranged Kw expression, we get an H plus concentration coming out at 1.404 times 10 to the minus 13 moles per decimeter cubed. So I'm just going to minus log that now. And it's coming out as 12.8524, so on, so 12.85. So for the last one, Remember, we're going to go backwards on this one. We're given the pH. We want to find the OH minus concentration. So the first thing we can do, if we know the pH, we can use this expression here. H plus concentration is 10 to the minus pH. So that's going to give us the H plus concentration, and that's coming out at 3.72 times 10 to the minus 13. That would be moles per decimeter cubed. We're told that this is being carried out at 298 Kelvin, so we know that the kW value will be 1 times 10 to the minus 14. And obviously that equals the two concentrations of the two ions multiplied together. Well, we know the H plus concentration. We don't know that, that's what we're trying to find. So if we divide the kW this time by the H plus concentration that we do know, we can calculate the missing OH minus concentration. When you feed those numbers in, you get an OH minus concentration of 0.0269 moles per decimeter cubed.